My name is Noah Hellmund, and this is my master's project. There are few natural systems that are as equally beautiful and terrifying to stand in than a wind-driven wildfire. This project was completed in collaboration between Western Colorado University and the Gunnison National Forest. In 2016, while working on a Type 3 Wildland engine on the Lassen National Forest, I had my first taste of how humans and biotic communities weather fire on the landscape in different ways. While the forest structure may change, other vegetation in time grows back from the fire, while human infrastructure is not so fast to recover. Seeing firsthand on the Klamath National Forest, an entire mountain community in a day transformed from a collection of houses and barns to a sea of debris-filled ash. The stories behind this project have many roots. A major one is knowing our Earth has many wicked problems that challenge everything we do as a species, trying to allow future generations to flourish in the cities and societies we have built. But by far the largest threat we have faced so far is climate change, and the many complicating factors that challenge our ways of life. In terms of fires, our summers and our fire seasons are getting longer, more intense. While fire seasons historically lasted just a few months, now some states are seeing seasons stretching throughout the whole year. Every few years, we see the fire records being replaced. Those changes are the stories being told by data. As presented in terms of numbers, it is easier to forget the costs behind these trends. When we hear of the next megafire burning hundreds of thousands of acres, it is important to remember those often include families' homes, communities, in addition to other critical infrastructure. These challenges are not just numbers. They are lives impacted forever. This challenge drove me to search for ways to increase the safety of communities in fire-prone environments. For this project, I was asked to create a suite of recommended fuel reduction treatments for 988 acres of fuel treatments in Taylor Park, Colorado. For anyone who doesn't know Taylor Park, it's a beautiful, pristine valley on the Gunnison National Forest. Its many miles of trails and roads bring significant OHV traffic through to Tincup, Colorado, a small historic mountain town that's deeply lodged in the Wildland urban interface, or the WUI. The Forest Service has proposed a widespread suite of vegetation management treatments throughout the area to increase security, ecological resilience, and support the local timber industry. My project's role within the larger efforts was to design and research a plan of proposed fuel reduction treatments, primarily lodgepole pine forest, in stands bordering or near private properties. I approached the project from a multidisciplinary background, considering a range of qualitative and quantitative measures of effectiveness for the proposed treatments. The factors influencing the potential for catastrophic wildfires on the Gunnison National Forest are a blend of environmental and human use challenges that together signal a significant threat to the security of small mountain communities deeply lodged in the WUI. Climate change is bringing longer, hotter, drier summers. Beyond climate change, there is a perfect storm of environmental stressors that pose a significant threat to lodgepole pine stands of Colorado. Especially prominent in Taylor Park is the spread of western dwarf mistletoe. Mistletoe is a parasitic, herbaceous plant that adheres to the stems and trunks of woody species, stealing nutrients from the host tree while slowly crippling the tree. Mistletoe impacted trees increase ladder fuels, carrying a ground of fire into the canopy, which in turn significantly increases the rate a fire can spread on the landscape. These concerns are compounded with the threat of mountain pine beetles making their way up the Taylor Canyon. In addition to the environmental challenges, are concerns of human infrastructure being built in the WUI throughout the area. Without the implementation of fuel reduction treatments, this area would be significantly threatened by the occurrence of a wildfire. It's not a question of if there is a fire, but rather when there is a fire. To create a data-informed approach for this project, my research team gathered on-the-ground data for the health of the forest and existing fuel levels, using intense common stand exams paired with a modified Brown's transects approach. With over 800 hours spent in the field, we inventoried standing trees and their health and counted the occurrence of woody debris at each plot. Over the field season, we collected data on 160 plots to create a strong understanding of the 43 stands within our project area. We then inputted those baseline data sets into FVS, the Forest Vegetation Simulator, which modeled changes in vegetation for the next 100 years based on different choices for managing the landscape. The treatments we were considering were: on the right side of this slide are the different treatment results modeled for the year 2040. Our baseline treatment options were, on one side, no action, and the other side, a clear-cut approach that removes all trees, only leaving a few standing trees for wildlife. Our middle considerations for treatments was for a pole harvest that removes all merchantable timber under 8 inches in diameter, and a hand-thinning treatment for areas too steep for traditional logging. The hand-thinning option is complemented with the use of mastication to mulch woody material from ground and ladder fuels. The other major treatment this research considered was a variable thinning approach. And the easiest way to understand it is a collection of all of these modeled outcomes on the screen. For example, in a stand you would have small clearings without trees, some patches thin moderately, and some areas thin from below. Once implemented, it begins creating a mosaic on the landscape that closely resembles the structure of a forest regenerating after natural disturbances. Because our model and calculations are not spatially based, we are unable to accurately model the effectiveness of a variable density treatment within our calculations. We still included it as a preferred treatment option based on input from local expert land managers with strong evidence for its success rooted in existing scientific understanding of forest management. Our forest inventory and modeled analysis told the ecological stories of a landscape rich with history. A wide range of stand conditions exists across the study area, ranging from fire-prone to relatively fire-secure. This range of conditions is reflected in my proposed suite of fuel reduction treatments for the area. As proposed, it includes 282 acres of variable thinning, 282 acres of hand thinning, and a smaller amount of the other treatment options, seen in this pie chart. The map on the right is a spatial representation of the treatments for the entire 988 acres of the study area. The light blue polygons are stands that were too steep for traditional logging operations. The pink areas were selected for variable density thinning for the diversity in ground conditions in close proximity to private property or larger roadways. The rest of the treatment selections were the careful consideration of the model changes in vegetation and fire potential for the next 80 to 100 years. Some stands are uniquely positioned so that it makes the most sense to implement a maintenance-based treatment plan that removes dwarf mistletoe-infected trees while letting the trees continue to mature. Once implemented, these treatments have the potential to increase the safety of local communities, while building knowledge of existing forest conditions so that land managers can make science-informed management decisions in the future. While I am soon starting a position working in Washington's timber industry, I hope to eventually return to a position where I can both research and implement practices that will help communities stay safe from fires. We know fires are only going to continue to get worse each year with climate change, based on scientific findings. But together we can give communities and first responders the best odds of making it home to their families when those large fires hit close to home. I want to take the time to thank the many people that supported this project at varying levels of involvement at the university, community, and agency levels. First, I'd like to thank Art Haynes, the Gunnison Forest silviculturist, for his support and mentorship on this project. His vision and experience have inspired my own career choices greatly. I would also like to thank Pat Medina, East Zone Fire Management Officer, and Dr. Jonathan Koop, my project advisor, who opened many opportunities for me to study fire ecology while here at Western. Additionally, I'd like to thank my research assistants, Justin and Amy, who spent hundreds of hours with me conducting fieldwork. A big thank you to the hundreds of work hours by volunteers, the timber crew, and local professionals that all contributed to the success of this project. I now invite you to return to the Zoom panel meeting for any questions or comments you have about